Okay, hopefully this is going to work. I apologize. Apparently we're having some issues with restricted mode. I'm going to text people to try again. Apologies. Sorry. Don't know why. That was weird, but hopefully we're back and not in restricted mode. Hey, we have a viewer. Is everything working properly now? If I get some knowledge dropped in the chat, let me know if things are working in the chat. Things good? No good? Waiting to see. Things working, not working. Maybe working. Working a little bit. There's no notification in the chat. That's not a good sign. That likely means people cannot see what's happening. Let me know, chat. Let me know. Let's take a look here. What's going on in general? We got anything happening here? Audio is good. Yeah, the mic looks like it's good, but no video, no anything. Technologies. We shall insert a sad emoji at this time. Let's find one that's extra sad. There it is. Sad emoji. Let me know if everything is okay, chat. Not entirely sure. Not entirely sure. Seems fine to me. Yes, we're in. Hooray. Thank you, chat. I'm supposed to be seeing your face now, correct? Yes, that's correct, Tor. Thank you. So seeing face. I guess earlier it was appearing that restricted mode was catching the video feed. It wasn't displaying properly. I've got 5 viewers. I've got 2 people saying yes. This is going to be awkward. The first 5 minutes of my video clip are now just going to be me sitting here troubleshooting. It was a different video on your channel for me. Yeah, I had one that I tried to schedule, and I think that one wasn't working properly. So I took that down, and I went live again, and I think it's working now. I think it's working. I think it's working now. Working, yes, I got confirmation that things are good. Yay! Hey, we're in business. Sweet. Sorry about that. I tried the scheduling feature that Jackson told me about, and I guess it just didn't, it got caught restricted or something. It wasn't working normally. So we shall put a happy emoji in the chat instead of a sad emoji. Cool. So we've got 7 people. It looks like things are good. It's 8:40. I want to get started. I know a lot of people view this later, so let's jump into things. Let's see if we can take a look. What I prepped tonight, I want to love your shirt. Thanks, Alexis. I want to take a look at the Chapter 2 review guide. I had originally prepped a few questions that I wanted to do on the live review, and I felt just after class today, it seems like more people are going to want a little bit more support in the review. So I figured I would do that tonight, and I'd save the questions for in class tomorrow, because then at least we have the answers to the review online live so that people can watch it later. So I am going to have time for Q&A, but I wanted to start by looking at the review packet first and kind of going from there. And if we have some time at the end to do some other stuff, we can certainly do that as well, okay? So first things first, let's just take a look at the topics that are going to be on Wednesday's assessment. Methods of factoring finite limits. So basically, goal is direct substitution, right? The goal of any limit is direct substitution, but sometimes things stand in the way of that. Sometimes you have to manipulate algebraically. Sometimes you have to look graphically. And sometimes direct substitution is going to fail, and you really have to consider like a logical case, like what happens if I try 5, a little bit above 5 and a little bit below 5, and so on and so forth. So just be aware those exist. Methods for evaluating limits: know how to use a function's end behavior. So know that a function's end behavior is really concerning yourself with an infinite limit. So if you're evaluating a limit as you go to infinity or negative infinity, you should really maybe think about end behavior models, okay? And we'll do some of those in the packet, of course. Know how to determine a function behaves on both sides of vertical asymptotes. Again, that's just testing values left and the right of a certain number. Know the continuity test, the easy 3-step continuity test, okay? So step 1 is basically making sure the limit exists, which is the limit from the left has to equal the limit from the right. Step 2 is making sure the function value exists. Step 3 is making sure the limit value equals the function value. So that's the continuity test, okay? Intermediate value theorem proves the existence that the function will basically hit a certain value in interval. You have to make sure you're continuous on a closed interval, though. And you have to state that. A lot of times the function is obviously continuous on a closed interval, but you must state since the function is continuous on the closed interval 0 to 5, and then you kind of get into it and make sure you credit the theorem at the end. So by the intermediate value theorem, a 0 must exist, for example, okay? And that's not in the review packet. So maybe someone in the chat, make a note of that. We can do an intermediate value theorem problem if we have some time tonight, or we'll do it in class tomorrow, okay? Max-min theorem basically guarantees the existence of an absolute max and an absolute min on a closed interval of a continuous function. So as long as this thing is a closed interval, you're guaranteed to have an absolute max and a min because it has to have endpoints. And so you have a restricted window to look at. Types of discontinuities, you need to know the difference between a jump, an infinite, a removable, and an oscillating. You need to know what they look like and how to determine them from a function. And remember, oscillating doesn't really come up too much, but I just wanted you to be aware. Extending a function, removing a discontinuity, so making sure you know how to remove a discontinuity and how to create an extended piecewise function that fills the hole of that discontinuity. And we can certainly do that if you'd like to see that later on today. Average rate of change is the slope formula, just y2 minus y1 over x2 minus x1, very straightforward. An instantaneous rate of change is your derivative, making sure you calculate the derivative at a value or just calculating the general derivative of a function. And know the shortcut. It's gonna help you. That's why I put the bonus video out there. You can't use it for justification on the test, but you can use it to make sure you know where your answer should be going, okay? So those are essentially the stuff. Can we do an oscillating one anyways, a quick one? I'm not really sure we have any in our textbook, to be honest, Ari. It's really just when you have a trigonometric function and the angle of the trig function has some type of discontinuity. Like I think the one in the video that I had was like sine of 1 over x. So obviously sine function has no problem, but then when you plug 0 into that function, it like the middle of it spazzes out and it just looks really weird. Like I said, I'm not even sure our textbook does any examples. I just wanted to show you, since we're talking about discontinuities, that is something that exists, even if we don't really consider it much in Calc 1, which is kind of what we're doing in our AP class. Okay, I didn't really have a specific question, but I know the ones students were struggling in class, so I'm probably going to focus on those, and I'll kind of bebop around a bit and spend, I know it's 8:45, I was running a little late today, maybe spend a bit of time doing that and then open up for Q&A, maybe like 20, 25 minutes at the end, okay? So let's start with number 1. Number 1's a great question. It says, write a function that meets the following requirements. So you have to understand what these are. So the first piece you have here is the limit as x approaches -2 has to equal -1. Okay, so that's no problem. That's just basically a limit from the left, limit from the right is -1 at both sides. However, the function value at -2 is 4. So that means the limit's going to be going towards -1, but the function value itself is plugged at 4. So just be aware that's going to happen. The limit as you approach 5 does not exist. And the limit as you approach infinity and negative infinity is 1, which is basically a horizontal asymptote. This is a horizontal asymptote. Okay. There's a lot of different ways to do this problem. And I think the easiest way that kind of to me is like a little cheating way is to just use a bunch of constants and link them together in a piecewise. And I think, that's fine. And you can do it a number of different ways. I'd like to maybe explore without it for now, just kind of looking at constants, because something I could do to make the problem more challenging is restrict you to no more than 2 pieces in a piecewise. And then the problem becomes very hard, or not very hard, but much harder than just simply linking 4 or 5 constants together. So let's assume that we want to try to do this in maybe as little pieces as possible. So the first thing I want to do is understand that I've got a limit value going to -2 is -1. I've got 5 not existing. And we got a point at -2. Okay, so the first thing I think I'm going to do in this problem is I'm going to put a infinite discontinuity at x equals 5. And I'm going to do this specifically at everything except -2, because I'm looking at this right here. And I'm thinking if we make x2, if we make this go to 4, and then I have my hole plugged in right here. So f of -2, this should be -2. F of -2 is going to be 4. And basically, this constraint is now satisfied. And now everything else has to be true as well. And I think the one thing I have to worry about is this. -2 from the left and -2 from the right have to equal -1. So if I make x minus 5 my infinite discontinuity, what I'm trying to do basically is try to get the limit to not exist. I'm thinking if I make an infinite discontinuity, which is an asymptote, I could make this thing hug positive and negative infinity from both sides, which would create a non-existent limit. I think it's a really easy way to achieve that. But if I do that, I need to plug something in the numerator to equal -1. And I think if I plug in -2, if I make this x plus 9, if I plug -2 in the numerator, it would be -2 plus 9, which is positive 7. In the denominator would be -2 minus 5, which is -7. I get an answer of -1. So this constraint is now complete as well. Interestingly enough, this constraint is also complete. Because if I wanted to test a number, let's say to the right of 5, I would have a number slightly larger than 5, -5, which would give me a very tiny positive, which would, as a result, if you divide by a very tiny number, you're going to get a very large number. And alternatively, if I try to check something to the left of 5, I'm going to have a little bit less than 5, -5, which would give me a very, very tiny negative. And as a result, this thing would blow up to negative infinity. So I have a vertical asymptote in which both sides are kind of hugging one side of the infinity. So they're going up, and you have a non-existent limit because the left and the right sides are different infinities. And so that's what we wanted. And I think we also satisfied this constraint, because this constraint basically says you have a horizontal asymptote at 1, right? If you go to infinity and negative infinity, this thing has to get really close to 1. But this is a rational function. And a rational function has horizontal asymptotes at the, if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is equal to the ratio of the leading coefficients, specifically 1/1. And so we have a horizontal asymptote at 1. And this is the answer that I feel is the most, I don't want to say like not cheating, like most sophisticated way, but this is kind of what I would expect. I wouldn't really, I would make sure that you would be able to build something like this rather than just a link of constants. And so I think this satisfies everything. So I think we're good with number 1. Let's check the chat. We're good now. The stream somehow appeared on a separate window entity from the other one. Weird. Are we okay? Are we okay? Are we going to be allowed to use constants on the test? Oh, no. Yeah, I feel like just follow the directions. I'll try to be really explicit in regards to the directions, but also, Ari, some problems just lend themselves to be a little bit, like what was a rigorous problem becomes more simplistic with the allowment of constants. And so I feel like if I was trying to just get you to do a normal problem, constants wouldn't really affect it. This one was meant to challenge you. This was meant to be tough. And I feel like you could kind of easily figure it out by just linking a bunch of constants together, or a linear in there too. But I kind of like that answer as the best. And I don't know if Anusha's online or if she's not, but she had a really good one in class today that I really wanted her to share. But maybe I can just pull it from her tomorrow in class. And Anusha is here. Anusha, you should share your answer in chat if you can. I know it might take a second to type up, or just take a picture and link it in the chat. But you created one that I thought was really clever. We can look at whenever you have a chance to type it in there. So we'll go back. Also, just wanted to check. The stream's not flipped, right? Because on my screen, the stream is completely flipped and everything is upside down and opposite. But I know that was the case last week, but it was flipped for me, but it was good for you guys. So I just want to make sure everything is good. Just give me a thumbs up in the chat. Make sure. Nope, the stream looks good. Thank you. Everything is fine. Beautiful. Thanks so much. All right, let's move to 2, and we can bounce back to 1 if Anusha has a second to show us her example. I thought it was a really clever one. So this one's different. It says write a nonlinear function So make sure you highlight that. That's important. That has a jump discontinuity at -1, but the slope from the right and the slope from the left at -1 approaches 3. Use the derivative shortcut to help you with this requirement. So this problem is really interesting because the problem is actually asking us to create a piecewise function. So it has to be nonlinear. So we're going to go ahead and kind of start with this again. And the slope from the left and the slope from the right have to equal 3 when x is -1. And I think that's a really good example of when to work backwards, because I know slopes to be derivatives, right? And I know derivatives to be, if I want to make sure I find the value of the slope at whatever point I'm trying to access, I plug it into the derivative. So what I'm essentially asking you to do is to create some kind of a function such that the derivative is equal to 3 when you plug in the number -1. That's kind of the goal. So you create a function such that take the derivative, and then you plug in -1, you get 3. But to make this problem harder, there needs to be a jump discontinuity. And so you can't just create one simple function to do it. You have to create 2 different functions such that when differentiated, the slope still equals 3, but the original functions have different function values to create a jump. And so let's kind of talk about how I approach this problem. Looking at the fact that the slope has to be 3, I'm thinking to myself, I need a linear function, okay? Oops, I was waiting a long time somewhere else. Oh, I'm sorry, Matt. It's my fault. We had a mix-up with the streams, and I tried to do a scheduled stream, but then when the scheduled stream went live, it was, for some reason, getting caught under restricted mode. So I redid it, and it's all good here. I apologize that you were waiting in the other space for a while. So we need the slope to be 3. So I really want to, I'm actually just going to kind of erase this for a second. And I'm going to piece together, I need the derivative to be 3x plus whatever. It doesn't really matter. But basically, I need the slope to be 3x. And if I plug a -1 in here, that's going to give me a slope of -3. So I'm actually going to alter my slope a bit, and I'm just going to stick a negative right in there. And that is going to be the appropriate derivative. So the question is, what function could I take the derivative of to get -3x as my derivative? Well, if I work backwards and I know my derivative shortcut, one such function could be basically, it's going to be, let's agree on one thing. When you take the derivative of something, the degree goes down, right? It goes down by 1. So if I go backwards and I want to build a function that I'm going to be differentiating, the degree is going to go up 1. So I know this thing's going to be quadratic. So the question is, though, if I use my derivative shortcut, if I bring the 2 down, it has to multiply by some coefficient to give me an answer of -3. And the answer there is actually going to be -3/2. Because if I multiply -3/2 by 2, the multiplication comes down and gives me -3 as my answer. But I can't have both pieces just be the same exact function. So what I'm going to do is I'm just going to create some arbitrary constant value, -3 minus 2. And that arbitrary constant value is basically going to change the function value when you're approaching -1. But when you take the derivative of the -3 goes away, and the derivative of the -2 goes away, giving you the slope that we needed. So the last thing is we just need bounds. So let's see. I don't know. Let's do greater than or equal to -1 and less than -1. I think this should work. So to the right of -1, if you actually plug -1 in the left piece and the right piece, you get different answers. But if you take the derivative and you take the derivative of each piece and you plug -1 into each derivative, it'll actually still give you a slope of +3. So I think this is one answer to do it. Let's read up on the chat here. Oh, sweet. Anusha's got her answer. I want to look at that in a second. Wait, can you explain again why you make it -3 and 3? You'll need to get 3 right. Yeah, so Will just answered it, but the idea is I need to plug -1 into the derivative, Ari. So if my derivative, if I do the math here, I'm just going to pick this one at random. And if I actually do the derivative here, I get -3x to the first power plus 0, whatever. And I need to plug -1 in here and get a slope of +3. And so that's why I had to negate it, because if I would have plugged in a -1 into my function without the negative, I would have gotten I would have gotten a negative answer, and I need the slope to be positive 3. So that's why I decided to negate it. All right, yeah, no problem. So that's 1 and 2. I mean, those are tough questions. Those are really the questions that I had anticipated people have trouble on. I want to open up a new page. I really liked Anusha's answer to number 1, and she was generous enough to type it. So I'm going to write it down in here. So she had f of x equals, let's see. Oh man, the chat is upside down and backwards now. I hope it looks good for you guys, but it's confusing me. Let's see. So she's got x plus 10 over x. So x plus 10 over x. And her restriction there is if x is less than -1. And then the next piece she had was x over 2. X over 2 if, and where we're going to be here, we're going to be x over 2 if -1 is, or x is between -1 and 5. So -1 less than or equal to x less than 5. I think I had that right. No inclusive on the 5. Yep. And then x over x minus 5. X over x minus 5. If last restriction, we're going to be greater than or equal to 5. Greater than or equal to 5. And I had a chance to look at this with Anusha today in class, and I thought it was a really clever solution. Let's pick apart that it's true. So I'm going to go up for a quick sec. I'm going to erase this madness. This is Sparta. I'm going to grab these, and I'm going to just bring it right down here. And I'd like to go through piece by piece and see if this worked. And this is what you should do on the test, because you could have gotten something completely different that I did, like Anusha did, and her answer could be fairly good. So let's check this piece by piece, okay? Piece number 1. As you approach -2 of the function, is the answer -1 from both the left and the right? Well, we have to be careful here, because left of -1, we're right here, right? And right, oh, sorry, no, we're doing -2, my bad. So -2 is in here somewhere. So both sides, it's in here, because it's left and right of -2 is always less than -1. So if you plug a -1 or a -2 in here, if you plug a -2 in here, we get -2 plus 10 is negative. Oh, wait, hold on. I did something wrong, because that doesn't work. What did I do wrong? X is less than -2. So we're defining left of -2 is definitely less than -1. And you plug in a -2 and you get 8. Oh, you get -4. I'm plugging in the value. Oh, what did I do wrong? You plug in -1. Any ideas, chat? This totally worked when I did it in class. Because this definitely is what I'm trying to do right now, and that works to give me 4. So where is it? Yeah, -2, it's definitely here, though. Did I copy the restrictions right? Less than -1. Yeah, that's what we needed, and it's x plus 10 over x. I don't know, Anusha. Did we look at it too quickly? Does it fail the first constraint? This definitely hits this one. 5 non-existent. It's definitely non-existent at 5. And then it has to have a horizontal asymptote. It definitely does, because exactly at infinity, we're going to be this right here, and leading coefficient over leading coefficient is 1 over 1. So the only one I'm hesitating on is that. Chat, any ideas? I think it fails that first restriction. Weird. Let me know, chat. X over 2 is what it's supposed to. X over 2 is what is supposed to hit this. X over 2. Yeah, and that'll give you -2 over 2. So yeah, I agree. So what Jackson is saying is we want that middle piece to be to satisfy that. And can we fix this somehow? Can we just change the bounds to -2s? No, that wouldn't work. No, that wouldn't work. It approaches -1 from the right, but not the left. So if we remove the restrictions over a bit, what if we move the restriction? I got to be careful. Can I change this to like negative? Can I change this to like 0? No, I don't want to do that. I want this piece to be at -2, right? So we want this to be like -3. And then this piece to just be like -3. Does this work? Did I ruin anything? I don't think I ruined anything, right? -2 now works from the left and the right. Check. 5 is still fine, non-existent. Check. Horizontal asymptote still exists for infinity, negative infinity, check. Yeah, because the negative infinity side is right here and here. So check. And then f of negative 2 is 4. I ruined that. Yes. Oh, no, I didn't. Negative 2 goes in the function. Yeah, it still gives me negative 1 as an answer. All right. Not good. Let's see what we got here in the chat. X plus 4 over x would work with the same restrictions, Amanda says. Let's check. Thank you, Amanda. Let's give it a try here. Let's keep the restrictions the same. And let's switch it. Amanda says x plus 4 over x. So we still have my horizontal asymptote at negative infinity because it's 1 over 1. Nice. Let's check the limiting value now, negative 2. As we go in, we plug a negative 2 in there, and we get plug a negative 2 in here, and we get negative 2 plus 4 is negative 2 over negative 2 is negative 1. So sorry, positive 2 over negative 2 is negative 1, exactly what we needed. This restriction of equaling 4 at negative 2 is still legit. I think we got it. Amanda, we did it. I'm sorry, I wrote x plus 10 over negative x. Oh, okay. Amanda's definitely works too. Let's look at Anusha had x plus 10 over negative x. X plus 10 over negative x for the top restriction, I'm assuming. So if you plug in negative 2 in here, you plug your, use a different color, negative 2 and negative 2. So that's 8 over positive 2 is 4. That still gives me the function value, not the negative one I'm looking for. Not the negative one I'm looking for. Sense. But does it approach negative 1 from both sides? Yeah, I don't think it does. I don't think it does. But we were close. With Amanda's help, I think we have what is a much more clever answer than mine. So let's put it back. There we go. Nice. So this is a good one. I think this is a really nice function that satisfies everything. It's very cleverly written, and I think it's cool. It's worth sharing. So thank you for sharing that, Anusha, and thanks, chat. Mean negative 2. Mean negative 2. Not sure what that means. Is negative 2 a mean number? Oh, I feel this would be some sort of hole that is defined it for. Since, yeah. I think all mine are horizontal lines. Yeah, I know, Matt, but I feel like it's cheating in a way. All right, let's move on from number 1. That was a good problem. We've got a little bit of time left. I do want to open it for Q&A. I'd say maybe number 4 is probably the next difficult, and then maybe some of the limits. But we can certainly, when we're in our Q&A for the last chunk of time, we can totally. You guys can ask me questions from the review packet as well. I'd like to do number 4, and then I'll kind of turn it over to you guys. Number 4 is an interesting one. It says, find the values of a and b such that the graph y equals ax squared plus b is tangent to the line y equals negative 3x plus 4 at x equals 1. So there's one thing we have to kind of remember, and that is a really important concept, that the slope of a tangent at the point of tangency is equal to the slope of the curve at the point of tangency. That's why we build these tangents, because the slope of this tangent is equal to the slope of the curve at that moment. So keeping that in the back of our minds and understanding that we are working specifically at 1, when x is 1, I need to somehow make the slope of this, oh, that was the worst boxing of a problem ever. I need to somehow make the slope of this equivalent to the slope of this. But this is actually a little bit easier than it leads on, because the slope of the linear is just negative 3. It's never changing. It's a constant slope. So really what I have to do is I have to battle out the slope of this thing, ax squared plus b. Specifically, I'm going to calculate it at x equals 1. Now, you can very easily use the shortcut to find the derivative. I'll show you the long way too. I don't want to be a hypocrite, but I'm just showing you the answer that we're trying to build towards is 2ax evaluated at x equals 1 gives you a slope of 2a. So that's the answer that we're trying to build towards. But let me do it out with limits, because it's good practice and also because it's what I would expect you to do. So let's go ahead and take this. And we're going to take this problem. Oh, it just randomly disappeared. Copy. Thank you. New page. Let's do this out longhand and see how it goes. Okay, so I'm asking you to calculate the derivative. So the derivative is the limit as h goes to 0 of f of x plus h minus f of x all divide h. But specifically in this example, I'm asking you to do it when x is 1, okay? So let's go ahead and plug in our values. So this is the limit as h goes to 0 of, I'm going to plug in a 1 plus h everywhere I see an x in my original function. So that's going to be a times 1 plus h squared plus b, all right? And that's just ax squared plus b, but I plugged in a 1 plus h. And now I'm going to minus f of 1. Now, if I minus f of 1, that's like me plugging a 1 into the x. 1 squared is 1. So it's just a plus b. All divide h. Okay? Verify I did that right. That looks good. And a plus b, because I plugged the 1 into x, and it just became 1 squared, which is 1. Let's go ahead and solve. So this is the limit. As h goes to 0, I'm going to expand this. So it's going to be a times 1 plus, and then h and h should be 2h plus h squared plus b minus a minus b over h. I see the chat blowing up. I'm just going to read it real quick. The shortcut for the derivative may be used throughout the test of exact problems. Does that mean we don't have to use limits for this problem? No, Matt, I would want you to use limits for this problem. Definitely want you to use limits. That's why I'm doing it out for you, just to show you. You can do whatever you want on scratch paper, but you have to be showing your answer with limits. So this is just, I'm going to just feed this a through really quickly. So this becomes a, and this becomes 2ah plus h squared times a, 2ah plus ah squared, I guess we'll call it. Get rid of the a, just so I don't have to rewrite again. And now let's see what we can cancel. So a minus a is 0. And then it looks like I have h goes to 0, b minus b is 0. So let's factor an h out. So we get 2a plus a h. And now a lot of people ask me in class today, Mr. Chapter, should I pull an a out too? There's no need. There's no need, because really I just wanted this to happen. And once that happens, I'm happy. Limit as h goes to 0 of 2a plus ah, which simply equals, a little bit of room left, plug the 0 in here. You get 2a, which is exactly what I wanted to get if I had done this problem using the shortcut. Right there. So 2a. So we get an answer of 2a, and now I basically need to set that equal to -3. So we're going to add another new page. Another new page, add page. So 2a equals -3, a equals -3/2. Okay, so I've got my first term, and I know that the coordinate point here is actually, the coordinate point is -1 or 1, 1, right? I'm just going to check the chat real quick, see what's going on. I think I'm just going to stick with limits. I'm using the shortcut wrong. Why does the shortcut lead to it being 2? Why doesn't the shortcut? Let's look at the function, Jackson. So b is a constant. So the derivative of the constant would be 0. Because if I use the shortcut, I can only treat one of the variables with respect. So if I take the derivative of 2ax squared plus b with respect to x, 2ax squared plus b, I don't know why I put a 2 there. Apologies, I'm thinking of ahead of the derivative. Ax squared plus b, only one of these can be a variable. So if I treat x squared to be a variable, that means I use my derivative shortcut on x to the second power, meaning it becomes 2ax to the first power. Everything else in the problem is just a constant. So that means that b is just 0. So you get 2ax plus 0. And I plug a 1 into x, and that's how I get 2a. Okay. So let's finish the problem now. There's quite a lot going on. I'm going to go find my work. Here it is. So I've got that a is equal to -3/2. And I know the function looks a little something like this, where you get y equals ax squared plus b. But I know a, I know x, and I know y. So I can actually just plug all this stuff in. Let's just verify. If I take a 1 and I plug it in my tangent, if I take a 1 and plug it in my tangent, that gives me the y value. If I just plug a 1 right here, it's just equal to 1. Y is equal to 1. So that's how I know the coordinate is 1, 1. So I'm going to take my function. Sorry for all the zooming. I hope you're not getting dizzy. I'm going to take my function y equals ax squared plus b. And plug a 1, plug in negative 3/2, plug a 1, and then solve for b. And so then 1 equals negative 3/2 plus b. And so if I add 3/2 to 1, I get 5/2 equals to b. 5/2 equals b. And so then I know my a and my b value. They are as follows: negative 3/2 and 5/2. Okay, so that question is really just assessing your knowledge of, do you understand that a slope of a tangent is equal to the slope of a curve at the point of tangency? So you slope the quadratic by taking this derivative, slope the linear by just looking at it, set them equal to each other, find a and b as a result. Okay, all right, let's check in with the chat here. Gotcha, derivative constant 0. B multiplied x is 0 if it explains helps. Which would come out to 0, 0, or 0. Yeah, so basically just goes right away. Nice. So we've got a little time left. I've got like 18 minutes or so. I want to turn it over to you guys. You can certainly ask me anything on the review packet. You can ask me anything generally, like just a random question you may have been having. We can do an intermediate value theorem. Whatever you feel like you need support in for the last little chunk of time is totally yours. So I'll turn it over to chat. Can we do number 3? Yeah, we can do number 3, Jackson. Let's give it a whirl. Okay. Just going to erase all this so it's not as busy. Actually, you know what? I'm just going to go fresh page. Let's just fresh page it. Copy, fresh page it. Okay. Paste. Let's look at this. All right, let's do number 3. So number 3 says, the distance traveled by a car in miles, given s of t equals this function, where the time in hours from 0 to 5, at what time in the 5-hour trip from 0 to 5 is the instantaneous speed of the car equal to the average speed of the car? Okay, so this is interesting. So what I actually have to do in this problem is calculate the average rate of change from 0 to 5. Okay, and in order to do that, I just need to do, I got to find out, so if my t is 0, what's my s of 0? So plug 0 in the original function, you get this, which is 0, okay? And then plug in 5, oops. And then so what's s of 5? So s of 5 is 3 times 5 squared plus 2 times 5, which is, what's this? So 5 squared is 25, times 3 is 75, and 10 more is 85. So 85. And now to find the average rate of change, you just do y2 minus y1 over x2 minus x1, which is going to give you an answer of 17. And since this is a rate of change, it's going to be, what is this? Hours and miles. Miles per hour. So the average rate of change from 0 to 5 is 17 on average throughout the whole interval. Basically, we need to set this equal to the instantaneous rate of change and find out what value of t this works for. Here's what you don't want to do, that a lot of students try to do in this problem. Take the derivative, plug in 5. But you can't do that, because in this problem, you don't know it's going to occur exactly at 5. You have to find the value. So your job is to find the derivative, the general derivative, set it equal to 17. That's how you find the answer. So what you'd have to do is you'd have to use your limits. You'd have to use the limit. So the limit as h goes to 0 of f of x plus h minus f of x over h. Don't plug in 5 for x. We're trying to find the value of x. And after you do this, I'll let you try the work because we don't have much time left. We only have like 15 minutes. If you do this, you're going to get your shortcut answer of 6t plus 2. So you then set the instantaneous rate of change equal to the average rate of change minus 2. 6t is equal to 15/6 would be your answer. And whatever miles per hour. Okay, and verify that's between, oh no, sorry, that's a t value. Whoops, t, time. Time is just hours here. This is not a rate. This is not a derivative. It's not a slope. You guys can read this is hours. It does not look like it. Hours. This is time. So we figured out that it's 15/6 hours. So a little over 2. Okay, so that's number 3. I hope that helps, Jackson. All right, I'm checking the chat for some questions. Can we do 3? We just did that. And then 7 part B, yes, we can do that. And can you also explain 7 part C? I'd be happy to. We're going to 7, the wonderful land of 7. I hope you guys are having a nice night, by the way. Thanks for tuning in. This is it's a good review session. I'm excited. I like this unit a lot. It's very procedural. It's very driven by, kind of the same concepts, which is nice. So 7a is you use the definition of the derivative to find the function. So I don't think you asked for that. So just B and C, no problem. So I'll just write the derivative here. The derivative is 1 over x plus 5 quantity squared, which is the derivative f prime x. So after you do all your fancy limit stuff, that's what you get. B, write the equation of the normal at x equals -3. So in order to write the equation of a normal, you have to first find the equation of the tangent, because a normal has a perpendicular slope to a tangent. So if we want to find the tangent, so the slope of the tangent, we just plug -3 into my derivative. Okay, so that's equal to 1 over -3 plus 5 quantity squared, which is equal to, what is that? So that's -3 plus 5, so that's 2 squared is 4, so positive 1 over 4. And actually, you know what? I messed my derivative up. Should be negative all that stuff because it's irrational, so it should be a -1 on top. It's the correct answer to part A. So you get -1 over 4 as the slope of your tangent, okay? That means the slope of your normal is the opposite reciprocal of that. So the opposite reciprocal, so slope, he got it, never mind, thanks. The slope of the normal is equal to, the perpendicular slope is positive 4, okay? So now what you have to do is you have to go through, struggling with the iPad mini and spatial orientation, apologies. Here, let's just grab this. And, oh, I had it. There we go. So let's copy you. I'm just going to go to a fresh page. I literally write one thing in the iPad mini, and it takes up the entirety of the page. Okay, sorry, we're back. Almost. Paste. No, you're not going to paste. You're going to be awkward when we have like 10 minutes left. That's cool. That's cool. That's good. Okay, whatever. I'll just continue without the problem. So we knew that the slope of the normal was 4. And I also know a coordinate point, right? Let's go back and look at the question. The coordinate was -3, and I have to find the y value. So if I plug -3 in here, I get 1 over -3 plus 5 equals 1 over 2. And that's a positive 2 because I'm talking about the original here. I'm not plugging it into the derivative, I'm plugging it into the original. So the y value is 1/2. The x value is -3. So the slope is -3 1/2. So the normal is y minus y1 equals slope x minus x1. And no need to put things in slope-intercept form. Point-slope form is completely appropriate. If you'd like to put it in slope-intercept form, I certainly won't take any points off. Just make sure you do it properly, or you will lose points if you do it. You make a mistake doing it, so just be careful. Okay, so that's B. I think we're good. Let's move on to C. So same question, C. And I'm just going to grab, if I can, I'm going to erase this. And I'm just going to see, you're going to let me just grab this question here. Yay. All right, you're going to paste? You're going to paste? All right, we're back. We're back. Part C, find the value of x when f of x has horizontal tangents if they exist. Horizontal tangent means the derivative needs to equal 0, right? That's what a horizontal tangent means, because the slope of a horizontal line is 0. So if I look at my derivative, f prime x, is -1 over x plus 5 quantity squared. The question is, how do I make this thing equal to 0? Well, I can't, because the only way to make a rational 0 is to make the numerator 0, right? But -1 can never equal 0. So we'd say since -1 can't equal 0, f prime x can't equal 0, thus no horizontal tangents can occur. Okay, so that derivative can never equal 0, which basically means you can never have a horizontal tangent. All right. Could you say it would be 0 at infinity and -infinity? The derivative? You can plug anything you want in this function. Oh, you're saying that if you make x really, 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 really big. Yeah, the problem, though, is that for a horizontal tangent to exist, you need to have a concrete point of tangency. You can't have infinity. Infinity can't actually be a value at which you're tangent. So it would need to be a finite number, not infinity. But I see what you're saying. If you do -1 divided by a real big number, the limit would approach 0. But alternatively, actually, the limit would approach 0, but that doesn't tell you anything about the function value. So that definitely would not work. You can't just say it's a really, really big number. Okay, cool. No problem, David. Happy to help. Chat, we got 8 minutes left. Is there anything on here? We got a nice function here. We got a removable discontinuity question, number 10. Number 8's really nice. It just goes through asking a couple of questions. We did 7. Man, the notes are a mess tonight. I'm sorry. I gotta get a bigger iPad. Number 4, we did nice. 3, we did some of these fun limits. You get stuck on any of these limits, you can do one of those. 5, whatever you guys want. Any requests in the chat? I'm just gonna pick one randomly and do it. Can we cover the limit problems? Yes, TJ Healthy. Let's do some limit problems. Let's do this first one here. So this first one looks not bad. Let's see if we can cancel the factors here. So it'd be x. Let's do the limit first. Oops. Let's do the limit as x goes to -1 of x minus 1 over x minus 1 x plus 1. This is problem 6a. 6a. These cancel, leaving you with the limit as x goes to -1 of 1 over x plus 1. This is a really neat problem because you know what? That factoring didn't help. Unfortunately, you can't directly substitute the -1 in the problem. So we need to use logic. Let's see if we plug a number in that's really close to -1, but from the left side. So it's like -1.000001. All right, if we do this, you're going to have 1 over a really tiny negative number, which would be really, really big negative infinity. So the left-hand side is actually going to go to -infinity. But the right-hand side, interestingly enough, the right-hand side, if you plug a number like -.9999, really close to -1, but from the right side, the 1 right here is going to be bigger than the -.99. So you're going to get a small, tiny positive, really small, tiny positive, which means this thing's going to infinity, which means this limit does not exist because you're approaching -infinity from the left and positive infinity from the right, which means you have a non-existent limit. That's kind of cool. Ooh, this one looks nice. You have the limit as x goes to infinity of a rational. And when you have a limit as x goes to infinity of a rational, you need to think n behavior model. So if you cross this out and cross this out, and you're left with the limit as x goes to infinity, let's simplify. So this becomes 1, this becomes 12x, right? If I cancel x cubed from both. And then I plug infinity in here, this thing goes to 0. Easy peasy. Okay, check in the chat, 6a. Yeah, that was the last one we did. Yep, all right, we just did 6a. We got an answer of does not exist because the limit from the left and the limit from the right were going to opposite infinities. So that one does not exist. Let's try this one. Another negative infinity. This is a rational, so n behavior model. So if we cancel this guy, we get the limit as x goes to -infinity of 7x over 1. And if you plug -infinity there, this thing's going -infinity because it's the denominator all canceled and went away. So this is just -infinity plugged in a function which goes to -infinity. Ooh, I like this one. We're going to infinity, so we have n behavior models apply here, right? And what's interesting is if you look at this numerator and you consider growing all the way to infinity, the x gets big, 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 big. But the sine x can only ever be 1 at most, right? So we chop it because it's not important. When we're talking about numbers as big as in billions, trillions, then the number 1 doesn't add anything to that. So we chop it. And on the bottom, same argument. We chop it. We chop the cosine because the cosine x is going to be at most 1, but the x is going to be really, really big. So this limit actually simplifies to the limit as x goes to infinity of x over x, which is just 1 because x over x simplifies to 1. And so that is just going to give you the answer of 1. That's a good one. What about this one? Okay. My theorem says I need to get a sine 7x over 7x situation. I need the 7x on the bottom. So I'm going to get rid of that. And I'm going to go ahead and see if I can let's take this 3, and let's drag it out front. Now, remember, it's on the bottom. It's in the denominator, right? So this is actually going to be 1/3 limit x goes to 0. So I've got sine 7x over x now. I need a 7 on the bottom. So let's multiply by 7 over 7. You always have to multiply by the same number top and the same number bottom, okay? Let's take this guy and move it here. I'm actually just going to just... And then this guy, let's bring out over here. And that's not 71. Now it's confusing. It's just 7/3. So this is 1. The answer is 7/3. 7/3 times 1. Because that's my theorem. The answer is 1. The limit as x goes to 0, sine of ax over ax. All right? Checking the chat. Whoops, I just realized I'm a minute behind. Oh, I'm sorry, Ari. I apologize. I know it's a little strange from your end. I've never actually watched one of these things before. So apologize if it's not cohesive. Limit as x goes to 0 of this thing. You know what I'm thinking? What if we just split this up? What if we just straight up split this up? Limit as x goes to, you see, I like sat up in my chair. I'm all excited to do this one. Limit as x goes to 0 of x cosecant x over x cosecant x plus limit as x goes to 0 of 1 over x cosecant x. All right, so let's just assume for a second that this thing goes to 1. Okay? And then let's play a bit. Let's line in the end there. Let's play a bit with the right side. So I have 1 over x cosecant x. You know what? I'm just going to do a little work on the side. A little doodling. 1 over x times 1 over cosecant x. Let's leave the 1 over x separate, and let's just play with the 1 over cosecant for a bit. So I know that the reciprocal of cosecant is sine, right? So this is really just 1 over x, and this is just sine x, right? Ooh, I have the limit as x goes to 0 of sine x over x. That's my theorem. That's 1. Hey, who makes these problems? 2 is the answer. 1 plus 1 just makes 2. So that's kind of neat. That was a fun one. So yeah, we're about out of time. So I hope this was helpful. Some of the problems that we didn't get a chance to do, we will certainly do in class tomorrow. And I've got some fresh ones as well for tomorrow that we'll kind of take a look at. But I hope this was helpful. Really, that was satisfying right there. Wasn't that nice, EJ? That was good. I hope you guys have a nice rest of your night. I hope, again, this is a good use of time. I'll kind of do another feedback survey and see what we could do to make things better. This one was a little bit more oriented towards the review packet, which I think is powerful. But at the same time, too, I'd also like to have time to just kind of explore some new problems that we haven't really had a chance to look at. So, yeah, thanks for tuning in. You guys have been a great audience, and I hope you have a nice rest of your night. I'll see you tomorrow for review, and we'll do a test on Wednesday. Take care.